Okay, so welcome to episode 3 of the Do-It-Yourself 8-Bit Computer series. We have basically two things we're going to talk about in this video. I'm going to cover the basics of digital circuits, and we're going to talk about how they are different from analog circuits. And then I also want to talk about the different logic families that you will find for integrated circuits that do digital logic. And specifically, I want to talk about the 74LS, 74HC, and 74HCT series of digital logic ICs and talk about their differences and why you might want to choose one series versus the other series. And in particular, I'm going to talk about why the 74HCT series is probably a good choice for working with 8-bit computer CPUs and peripheral chips, and for the type of circuit that we're going to be building when we build our do-it-yourself 8-bit computer. Okay, to understand how digital circuits are different than analog circuits, we should begin with a common principle applying to both kinds of circuits, which is the idea that voltages can represent information. And one important case of representing information using voltages is the concept of a signal where voltages vary over time. And analog circuits and digital circuits both use voltages to represent information. They just do so in different ways. So the fundamental characteristic of an analog circuit is that voltages can vary continuously, meaning that a voltage could have any value between a minimum and a maximum voltage. And this is useful for representing information where the values are going to vary continuously. So a good example of that type of phenomenon is audio, which is representing information about sound within a circuit. Looking at sound as a physical phenomenon, sound is pressure oscillations in an acoustic medium, such as air, that is caused by physical vibrations. So a sound waveform is essentially changing air pressure over time. So here is a representation of something like a sound wave, where the air pressure is oscillating over time. We have time on the x-axis, we have air pressure on the y-axis. And so the idea is we can more or less precisely represent that phenomenon inside a circuit, an analog circuit, as changing voltages. So again, over time, voltages are going to increase and decrease in direct proportion to the changing air pressure as measured by a sensor such as a microphone. So the advantage of analog circuits is that we can directly represent phenomena that have to do with changing values over time, such as our example of a sound wave. The disadvantage of an analog representation is that it is lossy. So it is not possible in general to exactly measure analog voltages or exactly reproduce analog signals. And every time you convert an analog signal to a different medium or communicate it from one device to another, you're going to degrade the signal slightly. So if you've ever worked with, let's say, audio cassettes, you know that you can't make copies of copies indefinitely before the audio degrades to a noticeable point. And so that's sort of the inherent limitation of representing information using analog voltages. So here is a very, very simple demonstration of what I mean by an analog voltage, meaning one that can vary continuously between a minimum and a maximum. So if we wire up a little voltage divider circuit here with a potentiometer, as we adjust the potentiometer, we should see a voltage change such that it can be measured by the multimeter here, which is in voltage mode. So you can notice right now it's at 0 volts, but as I turn the dial, I can make it take on any value I want between the minimum voltage 0 and the maximum voltage, which is the supply voltage, which is around, in this case, 5.2 volts. Now let's talk about digital circuits. Unlike in an analog circuit where the voltages vary continuously, in a digital circuit there are only two significant voltage levels, a low level and a high level. And the meaning of these two levels is subject to interpretation, but the two most common interpretations are the Boolean interpretation, where a low voltage means false and a high voltage means true, and the numeric interpretation, where a low voltage means 0 and a high voltage means 1. But regardless of how we interpret the meaning of the low and high voltages, the main thing to understand is that a single voltage represents one bit of information, meaning that it is one of two possible values. So one digital voltage alone by itself might not be very useful, but by combining multiple digital voltages, we can represent arbitrary information. So as an example, let's think about how to represent numbers, and specifically integers. So if we use our familiar decimal representation, then the different digits of the representation represent the powers of 10, in this case 1, 10, and 100. So if we wanted to represent the number 137, well, we would use 1, 100, 3 tens, and 7 ones. And each of these digits takes on one of 10 different values. So that's our familiar decimal number system. So if we want to represent the same number using digital voltages, then we need to change our digit representation so that instead of 10 different values, we have only 2 different values, because that's the two possibilities that we can distinguish in a digital circuit. So this leads to a binary representation, where each digit is now a power of 2, and the value of each digit is now either a 0 or 1. This is sufficient to represent any possible integer. So for example, if we want to represent 137, that is 1, 128, 064s, 032s, 016s, 18, 04s, 02s, and 11. So we can represent any integer using binary, and each digit can be, in the circuit, a digital voltage. So the disadvantage of digital circuits compared to analog is that they can't represent fundamentally analog phenomena, things like sound, directly the way that an analog circuit can. And if you do want to work with essentially analog data, you need to do some kind of encoding and decoding to convert between the analog and digital representations. The huge advantage of digital circuits is that they are exact. All of the data representations are exact, and they are lossless, meaning that we can take digital information, transfer it between devices, components, we can even record it, and we will never lose any information. Next, let's look at an example of a digital circuit. And in this particular circuit, we are going to test a NAND gate. What a NAND gate does is it has 2 inputs, 1 output. If both of the inputs have a high voltage applied, then we will get a low voltage at the output. Otherwise, if either input is low, we will get a high voltage at the output. And the way that we are generating these 2 inputs to the NAND gate are via these push button switches. One side of each switch is directly connected to the positive supply voltage. The other side of each switch is connected to ground through these resistors. And so when the switches are not pressed and thus they're open, the resistors pull these this node in the circuit and this node of the circuit to ground, and we get a low voltage. However, anytime you press the push button, it creates a path to the positive supply voltage, thus producing a high voltage at this node for this button and this node for this button. So the buttons then allow us to generate the inputs to the NAND gate. And what you can see is that right now, here's the little circuit on the breadboard, neither of the buttons is pressed. Therefore, both of the inputs are low. Therefore, we get a high value at the output, which is why this LED is lit. Essentially, the gate is currently in this mode. Both inputs are low, therefore the output is high. And if I press either of the buttons individually, you can see that the corresponding input voltage goes high, and these LEDs light up. But again, as long as one of the inputs is low, we're still going to output a high voltage, and this LED stays lit. It's only when I press both buttons at the same time that the output goes low, meaning that we're in this state, high, high, low output. All right, so now let's talk about logic families. And different logic families essentially have different ways of defining what counts as a high or low voltage. And there are parameters which are essentially thresholds for how low a low voltage needs to be and how high a high voltage needs to be. Okay, so there are input parameters, and these essentially determine from the perspective of the input to a logic gate or some other digital input, what is the maximum voltage needed for something to be considered a low voltage, such that essentially all voltages below this parameter are considered low. And then there's also a parameter that specifies what is the minimum voltage required for a voltage to be considered a high voltage, again from the perspective of an input to a gate or other digital input. And so essentially, if you want to drive the inputs of a chip belonging to a particular logic family, your low and high voltages need to be either less than the maximum input low or greater than the minimum input high. So here's a little diagram showing for the entire range of voltages between 0 and VCC, which is the common name for the positive supply voltage, the sort of where different voltages fall. And essentially, if you're below the maximum low voltage for the input, then you're good. That counts as a low voltage. Similarly, if a voltage is above the minimum high voltage, then you're also good. That counts as a high voltage. And then there's essentially this no man's land in between these two thresholds. And these are voltages that aren't either low or high, which is bad. And essentially you can cause erratic behavior from your circuit if you try to drive an input using voltages that are neither properly low or high. And then another important characteristic of logic families is for the outputs of the chips in that logic family, what is the minimum high voltage those chips will produce? And so in other words, you can always reliably assume that an output high is going to be at least a certain minimum. And that is an important characteristic, and we'll talk about that a little more in a moment. And so basically different logic families, some of the common ones like 74LS, 74HC, 74HCT, have different values for these parameters. And this becomes important if you are going to mix devices that belong to different logic families. If you're using exclusively devices that belong to the same logic family, you don't have to worry because the parameters are all going to be compatible. However, if you mix and match, you have to be a little bit careful. So in terms of low output signals, these basically are never problematic. You don't really have to worry about low output voltages. In general, they're going to pretty much always be low enough for any logic family they're going to count as a valid low voltage. Where you can run into problems is for high signals, high logic levels. And the specific case that is problematic is that if you have one device belonging to one logic family where the minimum output high voltage is less than another device's minimum high input threshold, then essentially the device that is producing the output signal isn't necessarily producing a voltage that's high enough to drive the other device's input. And in that sense, your circuit may not operate correctly, essentially because you may have a device that doesn't see another device's high voltage level as a valid high voltage level. All right, so now let's talk about the characteristics of these three logic families. We'll start with 74LS. On the input side, anything less than 0.8 volts is considered to be a low voltage. Anything greater than 2 volts is considered to be a high voltage. And in terms of the output produced, any low output will be at most 0.4 volts, any high output will be at a minimum 2.4 volts, and that is significant, the minimum output high voltage, because that's going to be significantly less than our supply voltage if we run the positive supply voltage at 5 volts, which is pretty typical for these types of circuits. Okay, so now let's talk about these two other logic families, 74HC and 74HCT. These are both CMOS logic, family. They're based on CMOS technology. They will have somewhat different characteristics. So the HC series is sort of the pure CMOS logic family. On the input side, any voltages that are at most 0.3 times the positive supply voltage are considered to be low. So at 5 volt supply, that means anything less than 1.5 is a low voltage. On the input side for high voltages, anything that is greater than 0.7 times the positive supply voltage is considered high. That means we need to have a voltage of at least 3.5 volts to count as a positive input voltage for 74HC devices. Again, this is at 5 volt positive supply voltage. And here is the key problem. 74LS devices don't produce an output voltage that meets this threshold. So you cannot really create a positive voltage using a 74LS device and have that be reliably considered a high voltage by a 74HC device. On the output side, we get nice properties from the 74HC series devices. Any low voltage will be at most 0.1 volts. That's quite low. And then in terms of high voltages, it's going to depend on the positive supply voltage. So typically, it's going to be something like at least 0.5 less than the positive supply voltage. So if our positive supply voltage is 5 volts, that means that our high signals are going to be at least 4.5 volts. And of course, that is plenty high enough to drive a 74LS device as input. Okay, so we'll talk about 74HCT series chips, and essentially these combine the best of both worlds. They are essentially CMOS devices and produce CMOS output levels. However, their inputs are compatible with TTL level outputs. So as you can see, the input thresholds for both low and high exactly the same as 74LS. But the outputs are very similar to the HC series. What exact values you get here kind of depends on which data sheet you read, but it's going to be similar. Maximum lows are going to be 0.1 volts, let's say. Minimum highs are going to be, let's say, 0.7 less than the positive supply voltage. So that would mean we would be guaranteed to get at least 4.3 volt highs at a 5 volt positive supply voltage. And what that means is either 74LS or 74HC can drive the inputs of 74HCT, and the outputs of 74HCT can drive the inputs of both 74LS and 74HC. So looking at this as a kind of compatibility matrix in terms of which outputs can drive which inputs, obviously each family, the outputs of each family can drive its own, the inputs of the same family. That, would be sort of ridiculous if that weren't the case. 74LS outputs, because of this, relatively low minimum high voltage that is produced, can drive 74HCT devices because they have the HCT devices have the TTL compatible inputs. They cannot reliably drive the inputs of 74HC devices. 74HC devices can drive everything just fine, and so can the 74HCT. So essentially, given this incompatibility between 74LS and 74HC that simply doesn't exist when you use 74HCT chips, that really does mean that 74HCT chips are, in some sense, the most generally useful for circuits involving these old digital logic devices because you can be confident that when you have any mix of TTL devices and CMOS devices in your circuit, you should have no problems with 748CT devices either being driven by arbitrary devices or driving arbitrary devices. All right, so one thing I should definitely mention while we're here is that this relatively low minimum output high voltage that is characteristic of 74LS and other TTL devices is very common for not only logic chips, but other types of devices that you might want to incorporate into your microcomputer circuit. And I've seen devices such as CPUs, memory devices, peripheral devices, having this relatively low minimum high output voltage. And so what that means is, as you build your circuit, you do definitely have to think carefully about, for a particular logic chip that you've incorporated into the circuit, are its inputs going to be reliably driven by whatever device is producing output connected to those inputs. And so that is another consideration that definitely weighs in favor of using 748CT logic devices, because you can confidently put them in the circuit and know that their inputs are compatible with all of the outputs of all the different devices that you're using, and of course that their outputs can drive any arbitrary inputs in your circuit. All right, so this is a good place to wrap things up, and obviously the summary here is that the 748CT series devices are going to be the most generally useful for these kinds of circuits involving old microcomputer hardware. So, as you kind of plan your circuit and are, shopping for devices, definitely look for the 748CT ones. In the next video, we will talk about combinational logic, basically circuits that you can build out of logic gates to implement, Boolean functions, and so that will, come, hopefully soon. I realized this video took a really long time. Things got kind of crazy in real life, but I am absolutely planning to continue the series, and it'll take as long as it takes. So I will see you next time.